this screencast, we're going to talk about where data comes from. Mostly, in an introductory statistics course, we learn how to make sense of data, turning raw data into useful knowledge, talk about how to crunch the numbers. But where does the data come from in the first place? In some programs, there are whole courses in research methods. Here we're simply going to introduce some of the problems and themes that arise in producing data. So we always start with the research question, something we're trying to answer, such as, is there a relationship between alcohol consumption and grades in college students? Or does smoking increase the risk of heart attacks? Does owning a home cause people to drive more safely? Does a new drug lower blood pressure? So we start with the research question. And to answer questions like this, we need to collect and analyze the data. So when we want to answer such a question, there are two major kinds of studies that we talk about: observational studies and experiments. In an observational study, the researcher observes variables of interest, just observes, surveying subjects, examining medical records, going out and looking at stuff, and records the results. The researcher does not intervene in any way. So as an example, students are surveyed about their study and lifestyle habits to see if students who consume alcohol regularly have lower grades than those who do not. Here the researcher simply collects and analyzes data, but doesn't do anything to affect student behavior. Another example, a researcher collects data from intersections with traffic lights and intersections with stop signs only to see what kind of relationship there is between the means of traffic control and accident rate. So it's important to realize that studies to determine relationships, or cause and effect relationships, don't have to be on people at all. In statistics, we use the language of population just to mean the whole group of interest, the whole group that we're interested in, but it does not have to be people. So that was observational studies. In an experiment, the researcher imposes a treatment on the subject by manipulating one or more variables of interest and observes the results, often comparing two or more treatments or two or more treatment levels to a control group. In a randomized experiment, subjects are randomly assigned to a treatment group. So for example, to see if a new drug lowers blood pressure, 1,000 volunteers with high blood pressure are recruited and randomly assigned to take the new drug or a placebo. Placebo is just a meaningless sugar pill. That's the control group for 6 weeks. Each subject's blood pressure is measured before and after the 6-week period. And any differences that we observe is almost certainly due to the drug, because the only differences between the people taking the drug and the placebo was the drug itself. They were randomly assigned. Now you can see it would be difficult to do an experiment to see whether alcohol consumption led to lower grades in students. You couldn't very well assign college students into a treatment group where they had to drink a lot of alcohol over the 6-week period and others who weren't drinking alcohol. That just would be impractical and unethical. Another example of an experiment, the researcher collects data on traffic accidents in an intersection with only a stop sign over a 6-month period, and then replaces this stop sign with a traffic light and gathers data for the next 6 months. So that way you can control for the kind of intersection it is and the particular intersections if at the same intersection you have stop sign or stop light over different periods of time. There are other things you have to be careful of here, but at least you'd be controlling for the actual location of the intersection. And of course you wouldn't just use one intersection. So we've asked this question before: children with bigger feet perform better on math tests. Is that evidence of cause and effect? And the answer is no. Children with bigger feet are older. Here's a less obvious example. Suppose a study were to show that students who are regular binge drinkers have lower grades than those who are not. Would that be evidence of cause and effect? So remember, the study showed association, but association does not imply causation. Association does not imply causation. And in fact, there's at least 3 different explanations of this phenomenon, of this association. One could be that binge drinking led to lower grades. One could be that students who are failing in school self-medicated by drinking. And a third could be that some outside factor, like depression or family issues, led to both drinking and low grades. So the association alone does not show cause and effect. We've said that many times. A confounding variable is one that affects the response variable and is related to the explanatory variable. The possibility of confounding variables always have to be considered in observational studies. So in that last example, the confounding variable would be whatever else is going on in the student's life. It affects the grades, and it could be related to the drinking. On the other hand, you don't need to worry so much about confounding variables when you're doing randomized experiments, because whatever the confounding variable is, you're distributing it evenly amongst both the control groups and the treatment groups. So if you can't do a study for the alcohol one, but as one example, maybe you find an association between people who eat oat bran muffins and heart attack risk. Well, is it the oat bran muffins causing the healthier hearts? Maybe, but it could also mean that health consciousness leads them to eat oat bran muffins and to exercise. So the exercise would be the confounding variable. On the other hand, if you take a group of people and randomly put them into two groups, a treatment group and a control group, where the treatment group is being told to eat oat bran muffins every day, and the treatment group is not told anything in particular, then the people who exercise are going to be distributed evenly among the two groups, and so any differences between the two ought to be caused by the oat bran muffins. So with randomized controlled experiments, you can worry less about confounding variables. So when you design experiments, randomization is crucial to avoid confounding the search for cause and effect. Placebos allow you to control for the well-known placebo effect, where people who think they're being treated have a response, even if the treatment is a sugar pill. Blinding or double blinding allows you to control for other biases. So blinding means that people don't know whether they're in the treatment group or the control group, and double blinding means the researcher doesn't know who's in the treatment group and the control group. So example, do people taking vitamin C have fewer and less severe colds in the winter? If people think they're taking vitamin C, then that might shade their expectations of what happens, and so they would report that the cold wasn't as severe, might not report a mild cold as a cold, all kinds of things. So you want to not let people know what group they're in, control a treatment when that's doable, and ideally the researcher doesn't know either. So 3 principles of good experimental design. Randomization, so randomly put people into a control group or a treatment group. Have a control group, so compare the treatment to a control rather than to nothing, and have a large enough sample size. So there are many kinds of experimental designs, and we'll just briefly touch on some of the issues or some of the kinds of designs. As I say, there are whole courses in these things. So in a matched pair design, you have pairs, well, for example, identical twins. If you had identical twins, put one in the treatment group, one in the control group, then any differences you can be pretty sure of the treatment. Or you could be your own control. For example, you might take a placebo for 6 weeks and then a new blood pressure drug for 6 weeks and compare the results. Block design, where you divide your population of interest into groups that might be affected by the treatment or who differ along the axis of the response variable. So if you wanted to see the effect of calcium on strength, you might, besides having a treatment group and a control group where some people took calcium and some didn't, you might separate them by age or make blocks based on gender so you don't get confusing information by having too many young people in the treatment group. There's also different kinds of observational studies. So a retrospective study takes data from the past and looks to see what it is. You know, what happened over the past, looking at medical records or surveying people about past behavior. And in a prospective study, researchers choose the subjects and follow them into the future. Prospective studies may generate better and cleaner data. So for example, if I want to know about students' study habits, it's kind of hard to ask them as seniors what their study habits were as freshmen. Whereas if I start them as freshmen and have them keep study logs, then I'll have pretty reliable data. On the other hand, subjects may act differently if they know they're being observed. So, what's the best, observational studies or experiments? Well, sometimes an experiment is unethical or otherwise impossible. You can't do an experiment to see if cigarette smoking leads to lung cancer. You can't do an experiment to see if binge drinking increases the risk of dropping out of college. On the other hand, observational studies are more difficult to control for confounding variables, but they do study subjects in a more natural setting. So observational studies, pros and cons. Natural setting, you can get many years of data without waiting many years for it, if you're doing a retrospective study. And you can conduct studies which would not be ethical to do by experiment. Cons, can't control for confounding variable. You can't specify levels of a desired treatment. So if you were interested in how alcohol affects grades, you couldn't have one group with no alcohol, one group with moderate alcohol, and one group with heavy alcohol, or at least it would be more difficult. And you can't as realistically or as determine cause and effect. It can be an indication, it can be evidence, but it's just not as strong evidence for cause and effect as a randomized controlled experiment. Experiment, you can control for confounding variables. You can compare multiple specific treatments or treatment levels in one experiment, and it gives strong evidence for cause and effect. But some studies that you might want to do would be unethical, or they might be impractical, and you have to have concerns about what's called ecological validity. So that means you might see results in a lab which wouldn't actually happen out in the real world. Psychologists sometimes bring people in and study them, and interactions between men and women. So how men and women interact in a laboratory setting when they know they're being studied, if you're studying, say, romance, dating, attraction, might be very, very different from how they'll interact out in the real world, say, in a singles bar. So you can study in a lab, but how well does that actually mirror the real world? So some warnings, got to worry about confounding and implications for causation with observational studies. We've said that before. Extending results inappropriately. You see something in a lab setting, or you see something that works within certain parameters, and you say, okay, that'll always work, or that'll work in other situations. You have to worry about variables interacting with each other. There's what's called the Hawthorne effect and the experimenter effect. Hawthorne effect is results may differ, or people may respond differently if they know they're being observed. And the experimenter effect, if the experimenter has expectations herself, then that may affect the outcomes. There are studies which show that if you tell teachers that certain groups of students are gifted, then that's what teachers will see, even if the students aren't particularly gifted. Ecological validity and how generalizable are the results. You have to worry about that too. And using the past as a source of data, well, the past is over, and maybe that's not what's going on now. And it also may not be as reliable. You have to worry about, when you're digging up data from the past, was it good data? It's hard to check. Okay, so we've talked about the different kinds of studies briefly and some of the pros and cons of the two major kinds. But how do we get our subjects or units of study? Suppose I want to know if watching screencasts ahead of time will improve student test scores. Can I just take volunteers? Well, that violates the randomization in an experiment. The students who are highly motivated to succeed in the class are the ones who are going to volunteer to watch these boring screencasts before coming to class. So that's probably not a good method. The best sampling is random sampling. This excludes confounding variables like student motivation. So we'll briefly talk about 5 different kinds of random sampling, or probability sampling it's sometimes called. Simple random sampling, stratified, systematic, cluster, and multi-stage. In simple random sampling, every group of the desired sample size is equally likely to be the chosen group. It's equivalent to putting the names or IDs of all possible subjects into a virtual hat and drawing them out until the desired sample size is attained. In stratified sampling, you break the population of interest into strata in ways that make sense for the study, and then sample from each group. For many kinds of opinion polling, it might be important to be sure people of diverse races, or ages, or religions are included in the study. So this is frequently the case in political polling, where you will break people into different races and then sample from each race, so white, African American, Hispanic, Asian, etc. And you also include them in the sample in the same proportions they are in the population. So whatever percentage of the US population is Hispanic, you choose enough people who are Hispanic so that their proportion in your overall sample is the same as in the population. In systematic sampling, you just find a system. So you sample every 1,000th product coming off your assembly line, or every 50th student, until you have the number you need for your sample. In cluster sampling, when the population is naturally divided up into groups, each of which more or less represents the whole population, you randomly choose some of your clusters to be part of your study, then sample from each cluster. Sample all of each cluster. So if you want to sample resident student population in Edgewood, you might choose a random sample of residence hall floors and then survey everyone on those floors. Or if you wanted to survey all Edgewood College students, you would take a simple random sample of classes, like Math 125 or Math 121 taught at 2 o'clock on Tuesdays and Thursdays, and go into those classes and then survey the whole class. That would be much easier than trying to find isolated people who aren't going to be all in the same place at the same time. And multi-stage sampling is just a combination of those previous methods. So you might divide the student population into strata, first-year students, second-year students, etc., and then within each group do systematic sampling, or else stratify by major. So that's a brief introduction to different kinds of studies and sampling.